Welcome to the fourth and last lecture in the lecture series on real and complex line arrangements. So today's topic is, first of all, we'll discuss a special class of line arrangements called nets in the complex projective plane. And related to nets, I'll try to describe some results of Libgober, Yuzvinsky, and Stephens. And afterwards, at the end, I'll mention some connection of complex line arrangements in general to the bounded negativity conjecture. Okay, so let's start with nets. So these are rather special line arrangements in complex projective plane. You could also do it real, but we'll stick to complex numbers. Okay, so suppose m is some integer, which is at least 3, and MNet in CP2 is actually m sets of m disjoint sets. Let's say A1 up to AM of lines in CP2 and a collection X of points such that the following two conditions are satisfied. So first of all, you want every point to belong to precisely one line in each class. So there are finitely many lines. Well, I didn't write, but these are finite sets of lines. Finite sets of lines. And for every point in X, you want it to belong to precisely one line in every class. So for every X in X, and for all I, each I, there is a unique line in AI containing this point X. Okay. And the second condition is if you choose two different classes of lines and pick one line from each, their intersection point is in X. So for every I not equal to J, the intersection of any line in AI with any line in AJ belongs to X. Okay, so in essence, this is a special line arrangement with some extra conditions. So let me draw an example. Here's a 3-net, a rather simple one. So you'll have 3 sets, and each will have 2 lines. Okay, and precise, it will be as follows. 4 points in X, so X will be a 4-point set, and okay, here are the lines in the first class. So each point should be contained in one of them. I mean, these are the 2 lines of A1. The lines of A2 will be some other partition of the points like that. So L21 and L22. And the third one is these 2. So L31, L32. One can quickly check that the conditions are satisfied. That means each of these 4 points is contained in precisely 1 line from each of these 3 sets. And furthermore, if you intersect 2 lines from different sets, the intersection is in X. Of course, there are some further intersections of lines within a class. For example, L31 intersect L32, and we say nothing about these. So these are not in point set X, and we don't consider them. Okay, now a simple lemma to start. So first of all, I claim that in this situation, if you have a net, then all these sets of lines must have the same number of lines inside. And if this common number is denoted by D, then the point set X must have exactly these square points. Okay, I mean, the proof is not too difficult. So initially, suppose that, and we can prove both parts together. So say AI has DI lines inside. I mean, a priori, let's give them different names. So D1 up to DM. Then there's a, I mean, the conditions say that there's a bijection between elements of between X and AI cross AJ for any I not equal to J, because any point should be contained in a unique line in I and a unique line in J, therefore you get the pair like that. Conversely, any pair of lines intersect in a point of X, so you get the maps back and forth. This provides you the bijection, and this implies that the number of elements in X must be dI times dJ, but this is for all I not equal to J, and recall there are at least 3 classes. So the only way to get this is if all of these numbers are equal. So di is equal to dj for ij, and let's say this number is d. You get both parts at once. Okay, so just an update on the notation. Okay, we say this is an MDNet, but since the number of lines in each class is a fixed number, it's reasonable to denote such a thing as a MDNet. So this says there are M classes of lines, and in each class of lines there are precisely D lines. Okay, now a basic question. So for which pairs of integers M and D, M being at least 3, can you have an MDNet embedded inside CP2? question. So for which pairs? MD with M at least 3 do we have? And in order to make it non-trivial, let's also say D is at least 2. Does there exist? An MDNet inside CP2. Okay, before saying something about this question, let's study the relation of nets and pencils of curves, a classical notion in algebraic geometry. So this is an apparently purely combinatorial definition of certain line arrangements, but it is closely connected to some other notion. So what's a pencil? So suppose in CP2 you take two algebraic curves. So say f equals 0 and g equals 0 are curves of the same degree in CP2. Let's assume that there is no common component, so no common divisor of the polynomials. Therefore, these meet at finitely many points, okay? And the maximum number, so assume no common components. Let's also assume for what follows, although this is not essential, that these two curves meet at the maximal possible number of points, which is by Bézout's theorem d square. So say they meet transversely, therefore they meet at d square distinct points. So this is the maximum allowable by Bézout's theorem if they have no common components. Okay, now the pencil through these two curves is a one-parameter family of curves. It is given by, let's say, mu times f plus lambda times g equals 0, where, okay, mu lambda are complex numbers, but of course, if I multiply both mu and lambda by the same fixed constants, it will give you the same curve back. So it's reasonable to take mu lambda itself to be in CP1. So that's saying you take two complex numbers, but you don't care if you multiply both of them by the same constant. Right, so this gives you some family of curves. It's, I think, worthwhile to draw a very basic example again. So take them both to be degree 2. Say are both plane conics, so they are degree 2. So this gives you a familiar picture from analytic geometry. So it could be, for example, these could be even real, like they could be two ellipses, for instance, but you can imagine the complex analog. Well, you begin to interpolate between these two polynomials. Now, any linear combination like this will still vanish on these intersection points. So these will be, these 4 points will be a member of every curve in this pencil. So you'll get different curves like this, but at some point this family will degenerate into 2 lines. If you keep pushing, if you increase the parameter, you'll begin to get some hyperbolas, although I didn't really draw it well. And even if you push further, these hyperbolas will merge in the middle and give you those 2 lines. And if you continue in the other direction, these will narrow down and eventually also give you these 2 lines. So if you forget the whole pencil and just concentrate on the reducible fibers, which are the lines, you precisely get a 3-2 net. Okay, now let's try to make this relation a little bit more precise. Okay, in a pencil, these nets seem to be corresponding to the completely reducible fibers. So where the combination breaks up into a product of lines. Okay, now a couple of definitions. First of all, this intersection f equals 0 intersect g equals 0, which is this set of 4 points in that picture, but you know, in general it's a point set with these square points. This is called the base locus of the pencil. And any member of the pencil contains the base locus. That's kind of clear. Okay, now let's now look at some point which is not in the base locus. So say denote base locus by B, let's say. And you suppose you have a pencil of 2 degree D curves. So pick any P which is outside this base locus. Now let's look at the condition for a member of the pencil to pass through P, which means this quantity being equal to 0. So now, since P is not in the base locus, either Fp or Gp, or maybe both, are non-zero. So at least one of Fp and Gp is non-zero. But then there's only one solution of this equation for mu lambda in Cp1. I mean, mu and lambda, then as a point in Cp1 must be equal to minus Gp f of p. So the consequence is, if this point is not in the base locus, then there is a unique member of the pencil which passes through this point. Okay, so it's a pretty clear picture. I mean, for the base locus, you have all the curves passing through the points, and for points which are not in the base locus, then there's exactly one of the members of the pencil. Okay, now let's go back to nets. Okay, say now A1 up to AM, and also the points at X is some MDNet. Okay, now I want to write some polynomials, so let Fi be the product of the line equations inside AI. So Li1 times Li d, there are d of them. So this is then a polynomial of degree d. Right. Now pick the first two, let's say, or any two of these polynomials. Let's pick F1 and F2. So consider the pencil. Let's say mu F1 plus lambda F2 through F1 and F2. So this will be some pencil of degree d curves. Then the base locus will exactly be X. Now a natural question is the following. There are these other polynomials, F3, F4, up to Fm, which also vanish on the base locus. So will you see them as some completely reducible fibers of this pencil? I mean, a priori, it's unclear. I mean, so there's some pencil that you form by the first two. I mean, these F2, F3, Fm, these other sets of lines are good candidates for this pencil to degenerate into lines, but does this always happen? And the answer is yes. So this is provided by a classical theorem in algebraic geometry. So the question is, do A3 up to AM occur as completely reducible fibers of this pencil? In other words, can you find mu I lambda I in CP1 such that each Fi is equal to this linear combination of F1 and F2? And what you only know is that these polynomials Fi's vanish on the base locus X. Okay, and the answer is yes. And the proof is by so-called Noether's AF plus BG theorem. This is a classical theorem from the theory of algebraic curves on a surface. Okay, the most, I guess, this general setup that we could use here is the following. So say Fg and H are homogeneous polynomials in 3 variables. such that degree of ages bigger than the degree of the other two. And furthermore, for all points in the plane, well, you could concentrate at what happens at P, which algebraically means you look at the local ring at P. So H lies in the ideal generated by F and G in the local ring. OP. So this is the condition. Then the conclusion is there exists homogeneous polynomials A and B such that H is equal to AF plus BG. So this is some kind of a local to global theorem. So you check the local necessary condition for H to be a combination of F and G. If it holds for every point, then it holds globally. That's what it says. And in our case, the intersections of F1 and F2 are assumed to be transverse. So the only condition for Fi to be in the ideal generated by F1 and F2 is that it vanishes at the base locus. So that's the connection between the theorem and our setup. Okay, so this discussion tells us that there's a very close connection between nets and pencils of curves. So the question that I wrote 10 minutes ago can be rewritten in the following way. So for which pairs MD does there exist a pencil of degree D curves in CP2 with exactly D square base points completely degenerating into D lines m times. Okay. Now, as we'll see, there are some restrictions on these numbers. So maybe the first thing to note is that if m is equal to 3, for every degree at least 2, you have examples. So this example aims to show that 3D nets exist for all d greater than or equal to 2. And the example I'll write is a Fermat type pencil. So we already saw a Fermat arrangement in the previous lecture. So this is a little bit different, but very close in spirit. So look at the following pencil. So here are our curves. Okay, so, well, this is our F1. And this is our F2. Now, F1 and F2 are products of lines. So F1 is the product of x minus zeta to the a times y, where zeta is some primitive d root of unity. So I could choose it to be, for example, e to the 2 pi I over d. And likewise for F2, of course. Okay, so we have two completely reducible fibers for mu lambda equals 1, 0, and 0, 1. But the upshot is there's one more. So if you set mu equals lambda equals 1, so mu lambda equals 1, 1 gives another. For an obvious reason of symmetry, so if you put mu equals lambda equals 1, you get x to the d minus y to the d plus y to the d minus c to the d equals x to the z minus c to the d, but of course this also decomposes in the same fashion. So this shows that this is a 3D net, and so we have a 3D net for every d. Now, maybe I should also remark in passing that this is not the only example for a 3D net. In a sense, there's a wealth of examples, and that's itself an interesting question. So can you classify all possible different 3D nets in some way? Okay. Okay, I'll not say too much more about 3D nets. Okay, now another example. This will be a 4-3 net. So 4 classes of lines, each containing 3 lines. Actually, this is the Hesse arrangement that we discussed before. So recall how this went. So take any smooth cubic let's say C inside CP2, and take X, the base locus, to be the set of inflection points of the smooth cubic, and there are 9 of them. So this is a 9-point set. And as we saw in the previous lecture, any line which passes through two of these inflection points passes through a third one. So diagrammatically, the lines must be situated in the following form. So you have one class of lines like this, let's say A1, and then a second class A2, yet a third class A3 like this, and also a fourth class. So then this is by this initial definition. I mean, if you don't want to think about the pencil a priori, this is by the initial definition, combinatorial definition of a net. This is a 4-3 net. Okay, and as I mentioned, this is rather special. It is unique up to projective equivalence. That's well known. Okay, now let's try to look at some higher values of m. So look at the time. So okay, before going on a break, I'll try to state the next result. So a result due to Libgober and Yuzvinsky shows that you cannot have m greater than or equal to 6. So it's a theorem first appear in a paper of Libgober and Yuzvinsky, then later in another paper of Yuzvinsky. It says part A, for an MDNet in CP2, we must have, one has m less than or equal to 5. So you cannot have a family which completely reduces 6 times or more into a union of lines. This is independent of D. Part B, if one of the classes AI is special, you can say a little bit more. So if one class AI contains just D concurrent lines, then M cannot be 5 either. And if two classes contain D concurrent lines each, then M cannot be 4 either. So if two classes AI, AJ contain D concurrent lines each, then M must be less than or equal to 3. Well, in the Fermat example, these 3 classes of lines, these products of lines, did contain 3 sets of concurrent lines, so this is kind of the best possible in this sense. Okay, so we'll try to prove this theorem, but maybe it's a good time for a break. Okay, so let's continue our discussion, and we want to prove this theorem. So we want to show that an MDNet cannot exist if M is 6 or more, and related results. So the proofs go through constructing an algebraic surface related to the pencil. So so here is how it goes. Well, I guess the basic idea, first of all, is, okay, the members of the pencil, if your point is not in the base locus, just one member of the pencil goes through that point. But if you are in the base locus, then all the members go through that. So in order to make things more uniform, we want to kind of change CP2 a little bit, so that in a new surface, just one member of the pencil goes through every point. So that would require replacing the base points by something else. And what technically one should do is, so blow up CP2 at the base locus. So what that will provide is the following. So suppose this is your P and you have some bunch of curves going through P. Blowing up P is an isomorphism outside P, but it replaces P by some exceptional divisor. And each of these directions is separated in this surface above. So then that would give you one member of the pencil passing through each of these different points in the exceptional divisor. And if you simultaneously do this for all the d square points of P, then this is true for the whole thing. Okay, so we get a surface S. Now, through every point of S, passes a unique member of the pencil. But then this surface S must fiber over CP1 itself. I mean, the fibration is sending a point to the mu lambda values for which it belongs to the pencil. Okay, so we get the following diagram. So we have this new surface S here. Let's say this is CP2. This is the blow-up map. So at these square points, and there's the fibration. Let's say this is pi. There's a fibration to CP1. Okay, let me try to sort of make a toy picture of the net as well. So you have your d square points. I'm drawing as if d is equal to 2, but this could work for any d. Now you have the members of the pencil. These are the completely degenerate fibers. These should really go through the points. Okay, and then you also have some smooth fibers. Actually, most members of the pencil will be smooth. So these different members of the pencil will be separated as fibers of this map phi. So most of the time, the curves that you'll see in a fiber will be smooth, but occasionally they will degenerate into singular objects, and at m places, they will degenerate completely into lines. So there are, for m points, Q1 up to Qn, these fibers over these points, phi inverse Qi, will be, well, okay, maybe saying a line may or may not be meaningful on S, but they will be of the rational curves intersecting transversely. So the problem, in a sense, is showing that if you ask for such a fibered surface with too many completely reduced fibers, that's not possible for some topological reason. That's what we want to show. Okay. Now, the proof follows from an easy topological invariant, which is the Euler characteristic. So we want to compute the Euler characteristic of S in two different ways. One by looking at the map pi, and one considering the fibration phi. Now, from the direction of pi, it is rather immediate. Each point blow up on a surface, well, the points are smooth points on the surface. This will increase the Euler characteristic by 1. So this will give you 3 plus d squared. Maybe, okay, I should say a few words about Euler characteristic of CP2. This is equal to 3. I guess there's a bunch of ways you could see this. For example, CP2 is the disjoint union of C2 and its line at infinity, which is a CP1. Now, C2 is a contractible manifold. It contracts to a point, so it has Euler characteristic equal to 1. And CP1 is complex projective line, which is a Riemann sphere. So this is just like a two-sphere. So its Euler characteristic is 2. And Euler characteristic is additive. Therefore, 1 plus 2 gives you Euler characteristic of CP2 equals 3. Now, then there's this additional d square, and that's the result of d square point blow-ups. At each point blow-up, for each point blow-up, we replace a point by a CP1. And again, a point has Euler characteristic 1, but CP1 is two-sphere, therefore it has Euler characteristic 2. So you're increasing the Euler characteristic by 1 at each blow-up, so this gives you 3 plus d squared. Now let's look at the other way, which is by using the fibration phi. Now, if we look at the picture a little bit, there are the smooth fibers, and also there are these reducible fibers. So we have to kind of estimate the contribution of each. So from the fibration phi, well, first of all, smooth fibers. Let's see. So these are Riemann surfaces of genus G, where G is given by the degree genus formula 1/2 d minus 1 times d minus 2. Then the Euler characteristic is equal to 2 minus 2g. Okay, so it's 2 minus d minus 1 times d minus 2, which if we simplify, the 2's cancel. This gives you, I suppose, 3d minus d squared. Okay, so that's the Euler characteristic of a smooth fiber. Now, the observation is with each, okay, there might be many types of singularities in the fibration. Well, we do have the completely reducible fibers that we have to take into account, but also there might be some other additional singularities, for example, a nodal curve at some point, etc. That's not so immediate to predict. But one important observation is each singularity will cause an increase in this Euler characteristic. So a simple example is a node. So at a node, for example, so the observation singularities increase Euler characteristic. Let's look at the example of a node. So this is some cylindrical part of the Riemann surface. What will happen is you will collapse a circle into a point, have something like that, which essentially is replacing a circle by a point. So the Euler characteristic of a circle is 0, but a point gives you 1. So that would cause an increase of 1 in the Euler characteristic, and similar for the others. Therefore, this is kind of the minimum you can get. Well, for the completely reducible fibers, that means a lot of singularities at the same time. So you would expect the Euler characteristic to go quite, I mean, it will increase quite a bit. And let's try to compute. So let's say we have a bunch of rational curves meeting transversely, let's say, first of all. So, yeah, so maybe I might have said something wrong. These don't have to meet transversely in general. They could meet in more special positions, but the transversal case will be kind of the best one in terms of Euler characteristic. Okay, we'll come back to that. Now, so these look like lines, but actually each of them is a CP1, and they're meeting at D choose 2 points. Therefore, Euler characteristic of this should be 2 times D, first of all, for the D CP1s, minus the intersection points you will be overcounting. Therefore, we have to subtract 1 for each intersection point. That means subtract D choose 2. So computation of this gives you 5t minus d squared over 2, which compared to 3d minus d squared is substantially higher, right? So instead of a minus d squared term, you have a minus d squared over 2 term. That means these degenerations to nodes let the Euler characteristic go quite up. For non-generic configurations, like 3 or more rational curves meeting at a point, this number will go even higher, up higher. So, but let's assume, let's look at this least case first of all. Now, also on the base, okay, if you take away these m special points q1 up to qm, you are taking away m points, so this will give you Euler characteristic 2 minus m. Now we are ready to estimate the Euler characteristic of S from below. Okay, if all the other fibers except these m very special fibers were smooth, that would contribute 2 minus m times 3d minus d square. But potentially, due to other nodal singularities and other things, it could go even higher. So, I mean, this is the least possible. And for these m special fibers, this is the least that we can have. So, for non-generic configurations, as I said, these numbers would go up and Euler characteristic would be greater. Therefore, this number, we computed in another way, 3 plus d square must be as large as this number. Same number. Okay, so we want to find a bound on m. Therefore, let's simplify this. Okay, if you collect all the coefficients of m on one side, it's d squared minus 3d plus 5d minus d squared over 2. This should be, okay, the leftovers on the other side are 3 plus d squared. And 2 times 3d squared minus 3d. This further can be simplified to m times, okay, we have d squared minus d over 2, if we simplify this. And on the right side, 3 times d minus 1 squared. D is greater than 1, so dividing by d minus 1 is harmless in the sense of this inequality. So this gives you m is less than or equal to 6 times d minus 1 over d, which is less than 6, proving the first part of the theorem. Okay, proving parts B and C are an easy exercise now. You only have to note that for B and C, note that if your special fiber is just like that, the irrational curves meeting at a point rather than generically, then the Euler characteristic is for this fiber is, let's see, you have a 2 contribution from each of these d rational curves. But now the number that you have to subtract is not d choose 2. You just overcount the points d minus 1 times. So it goes all the way up to d plus 1. And if you go through the same inequalities using this calculation, then you get parts B and C. Okay. Now, this result is nice, and it was improved some years later by Stephens in his PhD thesis. Showing that m equals 5 is also impossible. And a paper of Yuzvinsky in 2008 explains all the details very nicely. I'll just quote the idea. Well, okay, suppose you have a pencil again like that. One looks at the Hessian, so Okay, this is the pencil depending on lambda and mu. So f lambda mu is this good old pencil, lambda f1 plus mu f2 that we considered. Now, you can look at the Hessian, which is the determinant of the matrix formed by second derivatives. Now, if f is of degree d, this is a rather high degree curve. So this h gives you some degree 3d minus 6 in x, y, z. And the lambda and mu also appear 3 times in this determinant, so cubic in lambda and mu. So you have such an h, and the proof goes through this careful consideration of h. So in particular, you look at the vanishing locus of h, and a Noether AF plus BG type argument is applied to h, f1 and f2, and if you have 4 or more fibers, this argument works out very nicely. And if m is 5, this is strong enough to impose an impossibility condition on h. So that's how the proof goes, although I will not go into the details. Okay, so the last topic I want to discuss is some connection with an apparently different problem in algebraic geometry, where complex line arrangements seem to play some important role. This is the so-called bounded negativity conjecture. Okay. Now, for this part, let X be some complex algebraic surface over C. Algebraic surface over C. Okay. Now, I mean, it's kind of customary that we have possibly negative self-intersection curves on such a surface. So curves of negative self-intersection can appear, and this is not very esoteric. For example, if you just blow up one point in CP2, just as we discussed, okay, you have an exceptional divisor, and this exceptional divisor in this blown up surface, let's say this is X, has self-intersection -1. This is one of the maybe most classical examples. Another nice example would be to resolve a singularity, a singular surface. So let's do this for a certain type of singularity. So let's say we have the singular surface z to the power n equals xy, visualized as some affine surface inside C cube. This is an isolated singularity at 0, 0, 0. And this is a singularity of type a n minus 1. And if you resolve this singularity, you get a bunch of exceptional curves, and each of these has self-intersection -2. So this is another typical place where you see negative self-intersection. And I mean, it doesn't depend too much on the type of the singularity. You would get similar kind of thing in more or less all the resolutions. Now, then one might ask questions like how negative a curve can be on a surface. And the following conjecture seems to be wide open. Okay, so it says for every smooth projective surface X, over complex numbers, there is an integer p depending on the surface X, such that for all reducible curves C on X, one has self-intersection is greater than or equal to minus bx. So this conjecture is about saying that for a given surface you cannot get arbitrarily negative curves on the surface. Well, reducible here is kind of crucial. So reducible means no component has multiplicity greater than 1. Well, if you remove the word reducible, you could take a multiple of a negative intersecting curve and trivially violate this bound, but we are not interested in that. Also, another remark is that about this over C, it's known that in finite characteristics, so it's in positive characteristic, this conjecture is false. So there exist examples. But this is a difficult conjecture and seems to be completely open. Now, instead of this difficult conjecture, there were efforts concentrated around related questions. So, related problem. So how does this negativity of curves on a surface change under birational transformations? And even the simplest instances of this problem, for example, how is this affected if you blow up a finite number of points inside CP2? How about when, let's say, S points in CP2 are blown up? I mean, one has to be a little bit careful when stating a problem like this because of these immediate examples. Suppose you choose your S points on a line in CP2, let's say, and you blow all of these points up at the same time. Let's say this is L. You blow all of these points up, and you have a strict transform L in the blown up surface. Then it's easy to calculate that L squared is equal to 1 minus s. So it seems to be that if you blow up more and more points on the same line, you can get this number to be arbitrarily negative. But of course, this is a trivial example in a sense. So look at quantities like L square, the ratio of this negative intersection divided by the number of blown up points instead. This, in a sense, normalizes the problem. Instead of looking at absolute values of the negative self-intersections, try to calculate things like what is negativity per blow up, what is the what are the infimum of all possibilities? Well, this is a simple line, but you could generalize this question like as follows. Take C to be reduced curve in CP2, and C hat, it's strict transform after S blow-ups. So for example, can you say something about infimum of these self-intersections per blow-up over all possible reduced curves? The answer is unknown, and I guess it's unknown even if it is bounded or not. But there is some progress, for example, about the case when C is a line arrangement. In this case, there's a theorem saying that this infimum is not lower than -4. So you cannot go below -4 in the case of line arrangements. By the way, for other curves, this might still be a valid bound, but I guess it's unknown. Well, what the interest from our perspective is that I'll not do the details, but the proof is almost a direct consequence of here's the Bruce inequality, which I quoted last lecture. Follows from here's the Bruce inequality of last lecture. So this is a direct relation between what we have done so far and this problem. And also, in the previous lecture, we saw some very, very special complex line arrangements, and these do indeed give low values of this C hat square over S. Let me just write the values in order to finish the lecture. So for these special arrangements, Fermat arrangements, Klein arrangement, and this Wiemann arrangement, these C hat square over S gives you, well, this is a family of arrangements, remember, n equals 3D, and the number that you get is minus 3D square divided by d square plus 3, which is a little bit larger than minus 3, but as d goes to infinity, this goes towards minus 3. For the Klein arrangement, it is exactly minus 3, and for the Wiemann arrangement, it is calculated to be minus 3.36, if I'm not wrong. So, and this last one is kind of the record holder for now, among all line arrangements and all curves. So it's an intriguing question to ask whether you can go below this number by choosing some other configuration of lines or curves. And these are currently open questions. So that's ends the lecture series, and thank you very much for listening.